Hello everyone. This is lecture 4.4 of the GPU teaching kit. We're going to be presenting the tiled matrix multiplication kernel. The purpose of this lecture is to put our understanding of the tiled matrix multiplication algorithm to practical use and learn how to write a tiled matrix multiplication kernel. We'll study the kernel code for loading and using tiles for matrix multiplication. We'll see the practical use of barrier synchronization and shared memory in the kernel. After we finish the kernel, we're going to analyze the resource considerations and how the tile sizes and so on will affect the parallelism. And for this lecture, we're going to make a simplifying assumption that the width is a multiple of the tile size. In the next lecture, we're going to relax this so that the matrix multiplication kernel will have full functionality in the practice. In the next few slides, we're going to be introducing the ideas behind the kernel code for loading tiles of M and N for use in each phase. So we're going to focus on M first. This slide shows the idea for loading tile 0 of M for use in phase 0. Notice that the tile is of the same shape and size as the output tile in P, where this output tile consists of all the P elements being calculated by the current thread block. So a simple and logical design is for each thread to fetch or load a input tile element that is in the same relative position in the input tile as the output element is calculating in the output tile. So this is shown as an orange dot in the output P box and an orange dot in the input M box. And we see that these two orange dots are in the same relative position within each of these boxes. And if we look at the indices, we see that the orange dot in the M box has exactly the same row index within the M matrix as the output element. So we can just use that row index for the vertical index. For the horizontal direction, we see that the index is simply the x dimension of the thread index. So this gives us the two-dimensional index notation M, row, and Tx. Now we shift our attention to the loading of input tile 0 of N for use in phase 0. Looking at the top of the picture, we will be using the same simple design for loading the input tile 0 for N. We will use each thread to load an N element that is in the same relative position as the output element is calculating in the output tile. So this is shown as the orange dot in the N box. And we see that the column index or the horizontal index for N is exactly the same as the column index that we're using for P, whereas the vertical index for N is determined simply as the thread index of N in the Y dimension. So this gives us a two-dimensional index notation of N, thread index in the Y dimension, and then COL. Now we advance to phase 1. We need to load tile 1 of M. And we see that we're advancing to the second tile as we show in the second box in M. And we're still using every thread to load a element that is in the same relative position as its output element in the output tile. But here we see that the row index remains the same, but the column index need to be advanced by a full tile width. So this gives us the two-dimensional index for accessing the n element in tile 1. And we have row for the y index, and then 1 times tile width plus thread index in the x dimension for the horizontal index. Now we present the loading of tile 1 of n for use in phase 1. We see that we advance to the second tile of n, shown as the second to the top box in n. Again, we're going to be using each thread to load a n tile element that is in the same relative position in the tile as the output element is calculating in the output tile. We see that the column position of the element remains the same as the column of the P element, but we need to advance in the vertical or row index. The row index has been advanced by a full tile width. So that's why we need to add 1 times tile width to the thread index of y in the y dimension to form the new vertical or row index. Now we're ready to finalize the indexing for n and n elements when we load the tiles. From the previous discussions, we know that for each phase, we're going to need to advance the column index of n by a full tile width. So if we're in phase P, the column index of n is going to be P times tile width plus the x dimension of the thread index, whereas the row index remains the same throughout. And keep in mind that n is a dynamically allocated array, so we can only use one-dimensional indexing, so we need to linearize the two-dimensional notation into a one-dimensional linearized index by multiplying row with width of the matrix and add that to the column index. So this gives us the final one-dimensional index that we'll be using for loading the element of n in the tile. For n, we know that for each phase we need to advance the row index by a tile width. So if we are in a phase P, we need to add P times tile width to the y dimension of the thread index to form the row index, whereas the column index will remain the same throughout. So again, because it's a dynamically allocated array, we need to linearize the two-dimensional indexing into a linearized one-dimensional index by multiplying the row index by width and add that to the column index. So here we have the final indexing for the element of n when we load the tiles. Now we're ready to study a tiled matrix multiplication kernel. The first part of the kernel is very much the same as the basic matrix multiplication, with the exception that we added 2 additional declarations of shear memory arrays, ds underscore m and ds underscore n. These are tile width by tile width two-dimensional arrays that will be used to hold the input tiles for m and n. We are now ready to study the meat of the tiled matrix multiplication kernel. The for loop in the red box defines the phases of the tiled matrix multiplication kernel. Each iteration of the for loop corresponds to a phase of the tiled algorithm. The p variable indicates the sequence number of the current phase being executed. And within each phase, we will have every thread to load one M element and one N element according to the indexing scheme we introduced in the previous sequence of slides. And these M and N elements are going to be assigned into the ds underscore M and ds underscore N arrays using the y dimension of their thread index and the x dimension of their thread index. After those two statements, we need to execute async threads. This is because the threads in the same thread block may execute in different timing. So we need to make sure that all the threads have completed their loading their responsible M and N elements before any of them can continue to consume these M and N elements from the shared memory. After all the threads come out of the barrier synchronization, they will begin to execute the phase or a section of their inner product based on the shared memory contents. So once they completed that section, which is the middle for loop, they're going to all execute the barrier synchronization again. This is because we need to make sure that all the threads have completed their inner product calculation based on the shared memory contents, so that we know that no thread will need the current shared memory contents anymore. So once all the threads have reached the sync threads, we know that the current contents of the shared memory arrays ds underscore M and ds underscore N are no longer needed, so that we can go to the next iteration of the for loop, which means that we're going to be loading the M element tiles and N elements for the next tile or next phase. This is very important because if any of the threads moved ahead to load the next phase M and N elements, it may accidentally override the M and N elements that some other threads are still yet to use. So that's why this second sync thread barrier is very important for the correctness of this tiled algorithm. Once we completed all the iterations of the phase for loop, then we will come out and every thread will be writing their output value into the P matrix. Now that we have seen a tiled matrix multiplication kernel, we can do a little bit of analysis on how we should set the tile size and therefore the thread block size for this kernel. We see that each thread block should have many threads. If we use tile width of 16, we have 16 times 16, which is 256 threads in each thread block. If we use tile width of 32, we have 1,024 threads in a thread block. Intuitively, the more threads a block, we should have more parallelism and more scheduling flexibility. But we'll come back to this point later. If we use a tile width of 16, in each phase, each thread is going to need to load two elements, one M and one N, and there are 256 threads in the block. So we will be making 2 times 256, which is 512 floating point loads from the global memory. Once the two tiles are in the shared memory, each thread is going to perform 16 multiplications and 16 additions to complete the phase of inner product calculation based on that tile. And we have 256 threads involved, so we have 256 times 2 times 16, which is 8,192 multiply add floating point operations for the phase. To summarize, we have 16 floating point operations for each memory load, which is 8,192 divided by 512. This is a very good ratio. This brings us much closer to the ability to support the execution near peak throughput for a processor. If we use a width of 32, in each phase, each thread is going to still load 1 M and 1 N element, but we have 1,024 elements in the tile. So we're going to have to load 2,048 floating point operands from global memory. Once these elements are of the tiles are in the shared memory, we have each thread to perform 32 multiply and add for the inner product, and we have 1,024 threads. So we will be making 1,024 times 2 times 32, which is 65,536 floating point multiply add operations. Now we have 32 floating point operations for each memory load, which is 65,536 divided by 2,048. And this is even better. We have essentially very, very close to the ability to support full floating point execution throughput for a typical GPU today. Although the previous slide seemed to indicate that a tile width of 32 elements is better than a tile width of 16, other resource constraints in the streaming multiprocessor may reverse that indication. For example, if we have a streaming multiprocessor with 16 KB of shared memory, for the tile size of 16, we know that we need to accommodate 2 tiles of 256 elements each, and there are 4 bytes in each operand element. So this requires a total of 2 KB of shared memory per thread block. With the 16 KB of shared memory, we will be able to accommodate 16 KB divided by 2 KB, which is 8 thread blocks. These 8 thread blocks will be able to give us plenty of parallelism and scheduling freedom. For example, if we have 2 loads from each thread in these 8 thread blocks, we'll have 2 loads per thread, 256 threads per block, and then 8 thread blocks. We will have a total of 4,096 loads for loading their input tiles. And this gives us plenty of parallelism for utilizing the memory channels and banks. Now let's look at the next tile width of 32. This would require 2 tiles times 32 times 32 elements in each tile, and then 4 bytes in each element. So this requires 8 KB of shared memory per thread block. With 16 KB, we should be able to accommodate 2 thread blocks. Unfortunately, in most of the current generation streaming multiprocessors, there's a thread count limit of 1,536 threads. So this will limit the number of thread blocks to 1, since having 2 thread blocks will require 2,048 threads, which exceeds the thread count limitation. So as a result, we will end up with only 1 thread block of for the case of a tile width 32. To make it even worse, because we have 2 sync threads in each phase, the sync threads can reduce the number of active threads, because many of these threads will be waiting for other threads to reach the barrier synchronization. So having only 1 thread block can really become a problem, because many of the threads could be just, in that thread block, could be just waiting at the barrier synchronization point. So in this case, having a tile width of 16 can be much better than having a tile width of 32, because there are more thread blocks that will allow us to alleviate the problem of having most of the threads waiting at the synchronization. Some of the thread blocks will be waiting at the barrier synchronization point, while others may be loading their input operands and performing computation. So this gives us a very good example of the interaction of resource constraints may limit the tile size of our tiled algorithms. Lecture 4.4. Thank you.